Okay, this should be physics class. This is week 2-5. Tomorrow is Monday, December 7th. This video should be Physics25ABlake. And I'm going to take care of a couple items before I go into this. I went back into the week 2-4 flip chart, and I got this diagram out of the book and put it in here. And this will help you maybe figure out if the work is positive or negative. That's not something I'm going to make a big deal about. But if both your force and your distance are positive, that's positive, and then this force would have a component this way, and then these would add up. This force would have a component this way, and these would add up. If both your force and your distance are negative, which they don't have shown here, then it's positive, because a positive number and a positive number is positive. A negative number and a negative number is positive when you're multiplying them. But if one of these is positive and one is negative, then you get a negative work. I guess I'm not so thrilled with this picture after all. Maybe I'll get a different one. This one tends to focus on the components, but I see what they're doing here. It's just not making the point I wanted to make. All right, anyway, let's go on. Either at the end of week 2-4 or at the beginning of week 2-5, depending on if you're gold or green, you need to do this lab to get to determine the spring constant. So we will do this Monday for green, and then on Tuesday for green we have to do a power lab. So you're going to do a lab both days. So make sure, green, that you are catching up with the problems here in the book outside of collecting and processing data in class. Okay. So, power. What is power? Power describes how fast work is done or energy is transferred. I think this could be done with a mechanical energy explanation, but I'm going to go old school and keep it the way I've done it and keep it the way the book has done it, but it's not perfect. So you can get power, and by now you should know how to calculate work. It's force times distance. Work divided by time, or force times speed, which is not as often done, but it works. Let me show you why that works. There's so much that we can do if you can get the the units to work together, you can do it. Power is in watts. So this line here is units. Watts is joules per second because it's work divided by time. You'll run into this when you go to do your lab, the power lab. Work is force times distance. We've already established that. So it's newtons times meters. So the units for work is newtons times meter divided by second, but so is the unit for when you go with force times speed. It's newtons times meters per second. So here I've got the speed in meters per second and the force in newtons. Here I've got the work in newtons times meters per unit of time in seconds. And my color coding shows work over time versus force times speed. But it's the same units. So the imperial English for power is horsepower. I think there's 746 watts in a horsepower. And the metric unit is joules per second, and it should say or watts. Let me put watts in there. So my watts is equal to joules per second. Joules per second. Let's continue. Okay, Mike, I like to put this picture up and ask a question about it. Is the fuel consumption the same to plow the whole field? Here I've got old classic tractors. Sometimes I like to ask my students who think they know about farming about these tractors, and I always stump them on there. Oh, it's a John Deere. What's that? Okay, what's that one? Anyway, this is John Deere. If you plow 100 acres this way, two guys out there in little tractors taking hours to do it, versus 100 acres this way, which you could do in, I don't know, it wouldn't take very long. More than an hour, but I mean, if you could just go in, at 43,560 square feet in an acre, this could pound out an acre in minutes. So, you know, a couple hundred minutes maybe, a few hours. This would take, for 100 acres, it'd take days with like this. Is it the same work? Well, all of the dirt gets turned over, so yes, it's the same work. And if it's the same work, assuming the efficiencies are both good, it's the same fuel consumption. As a matter of fact, this one might be more efficient than this one. But let's say it's the same. To get the dirt does the same amount of work. And let's say these are all the same width and depth of plowshares on the same soil. It should be the same work done. The difference is the time. This is much faster. So you're doing the work at a greater rate. Now, here's another way of looking at power. Let's observe two different speeds on the same hill. So you got a hill. Actually, I've got three different speeds. Same hill. If this vehicle has higher power, it can go farther up the hill. Let me try that again. If this vehicle has a low power, it doesn't make it as far up the hill. You'd have to downshift. Maybe this is like a camper going up a hill when you're on vacation and it's in the slow lane, or a truck or something. If you are going up the same hill, a low power vehicle results in a slower climb. You're not going up as fast. If you have more power, you can climb more of the hill in that period of time and gain more gravitational potential energy. If you have a lot of power, you can climb even more hill, more mountain at the same period of time. So if you have a higher power, this will result in a faster climb up the same hill. But you still climb the hill, it just takes more and lower power. You got to shift down to a lower gear, maybe. Now let's look at the same speed on different hills. Same speed, different hills. The other ones weren't the same speed, it was the same hill. This is different hills. Same speed. So here I have different hills where my vehicle goes 10 meters per second, 10 meters per second, 10 meters per second. This hill is steeper. So if you have the same weight of vehicle on it, it's going to have a greater downhill force that you have to overcome. So the forces are different. So the forces increase as you go down, speed stays the same. So with a less and less steep slope, the downhill force decreases. Three different hills. Countering the downhill force with an equal and opposite driving force at a constant velocity just results in the lower force over a longer distance. So what's going on here is the force is less, but the distance is more. Oh, no, sorry. It says the work is the same. No, I don't have this written up here, but if I have work as force times distance, here's what I meant to do. You're going to climb the same hill. You're going to get to the top of the mountain, but it's going to be three different sides of the mountain you're going up. So the distance is the same. No, sorry. On this hill down here, you go more distance, but you have less force and you get the same answer. There we go. Less force, more distance, same work. Same gain in potential energy, no matter which way you go up the hill. But this time, if the speed is the same, this one, a longer distance, takes more time and less power. So maybe you're pulling a camper or whatever, you can go 10 meters per second. And if you go a long, slow climb, you can go your 10 meters per second and get up the hill. It's going to take more power to get up a steep hill. Same work's done. This one's quicker because you're not going as far. Here you have your force times your speed is your power. If my speed stays the same, and my force gets bigger to counteract the downhill, then that more power one is going to be required to go this one, which will take less time, because if you're going 10 meters per second, this takes less time than this, takes less time than this, if they're all 10 meters per second. That's a lot to think about. Which brings us to the conceptual challenge about the mountain road. The question was, I'm on page 187, many mountain roads are built so they zigzag. Discuss the advantages of a design from the energy conservation and power viewpoint. The amount of work to get to the top of the mountain is the same. What you're doing is making that an inclined plane. You are lowering the steepness. Instead of going up the mountain, you're building a road that goes more at an angle, or less of an angle if you prefer. And this increases the distance traveled and decreases the force required. So as the less steep slope is used, distance increases, the downhill force decreases to a manageable level for the vehicle, and this will spread the work out over more time. It's going to slow down your progress up the mountain, but it makes it possible to do. Question 2 asks about a light bulb and if a light bulb has power. Now, what a light bulb does is it transfers electrical energy to thermal energy in a filament, which transfers a lot of that and some of that energy out as light energy. And all it does is it consumes 60 joules of energy into some light energy and most thermal energy every second. We're going to talk more about this later. Okay, we're going to do a horsepower lab. And in the horsepower lab, if the weather's fit, we'll go outside and we'll put a bowling ball over the fence. It'll take 2 people. And between you, 2 of you will calculate the horsepower, but we'll drop it over the fence and then drop it back over the fence and drop it over the fence and drop it over the fence. And we'll see how many times we can do that in like 30 seconds or a minute. And we'll measure the weight and the number of times you do it and how high the fence is. And we'll derive all the other data and we'll figure out the horsepower it takes to do that. We'll talk about that in class. I've got a handout for you to do that. Okay, let's go to page 81 or 188 and take a look at this first one, page 188. Starting the problems on power. And we've got time to do 1 or 2. Okay. A 1,000 kilogram elevator carries a maximum load of 800 kilograms. A frictional force prevents you from going upward the way you'd like. What is the power in kilowatts the motor must deliver to lift the fully loaded elevator at a speed of 3 meters per second? So what you've got is you've got a force downward of gravity on the elevator, so the weight of the elevator. And you've got force of gravity on the people in the elevator. which is mg, and that's 800 kilograms. And you have a frictional force of 4,000 newtons. So you've got mg is in newtons, mg is in newtons, and 4,000 newtons. Now power is work times time. The work in this case is weight, force, times distance. And we can substitute all that. So let's find the work for well, it looks like I found the force first. So I had 1,000 kilograms times 9.8 for the elevator, 800 kilograms times 9.81 meters per second squared for the people, and 4,000 newtons of friction. You add all this up in your friction force, this term is 21,640 newtons. Now we've got to go that force times the distance and divide by time to get power. So you are going up 3 meters. Here's my force, distance of 3 meters, and you're going to do that every second. If it's 3 meters per second, I think that's what it says. It's 3 meters every 1 second. Multiply out, and it's a 66,000 watt elevator. Okay, well, number 2, I've got this little diagram. Work is kinetic energy, is potential energy, work, kinetic energy, potential energy. If there's no friction, and we can even account for friction using this, this is the work energy principle. And so we can find the work to accelerate this car if we know it's kinetic energy and set that equal to the work. We know when it's done, it's going 10 meters per second and it weighs 1,500 kilograms. So when we multiply out, it's kinetic energy, 75,000 joules. That means you put 75,000 joules of work into it. So then you just divide work by time, and it comes out to be 25,000 watts. The next video will be Physics25ABlake.